An operating system provides services to both the users and to the programs. It provides programs an environment to execute. It provides the user the services to execute the programs in a convenient manner. The following are a few common services provided by an operating system. Program execution. Operating systems handle many kinds of activities from user programs to system programs like printer spooler, name servers, file servers, etc. Each of these activities is encapsulated as a process. A process includes a complete execution context, like code to execute, data to manipulate, registers, operating system resources in use. The following are the major activities of an operating system with respect to program management. So operating system will load the program into memory, executes the program, handles program's execution, provides a mechanism for process synchronization, process communication, and provide a mechanism for deadlock handling. I/O operation. An operating system manages the communication between user and the device drivers. I/O operation means read or write operation with any file or any specific I/O device. Operating system provides the access to the required I/O device when needed. File system manipulation. A file system is normally organized into directories for easy navigation and usage. These directories may contain files in the other directions. Following are the major activities of an operating system with respect to file management. The program needs to read a file or write a file. The operating system gives the permission to the program for operation on file. Permission varies from read-only, read-write, denied, and so on. Operating system provides an interface to the user to create or delete files, to create or delete directories, or to create the backup of the file system. Almost all operating systems have a user interface, UI. This interface can take several forms. For example, a graphic user interface, the interface we see in Windows system with a mouse that serves as a pointing devices to direct I/O, choose from the menus and make selections, and a keyboard to enter text. iPad, iPhone, they provide a touch screen interface, enable users to slide their fingers across the screen or press buttons on the screen to select choices. Another option is a command line interface, which uses text commands and a method for entering them. The operating system handles routing and connection strategies and the problems of contention and security. The following are the major activities of an operating system with respect to communication. Two processes often require data to be transferred between them. Both the processes can be on one computer or on different computers, but are connected through a computer network. Communication may be implemented by two methods, either by shared memory or message passing, in which packets of information in predefined formats are moved between processes by the operating system. Error handling. Errors can occur anytime and anywhere. An error may occur in CPU, in I/O devices, or in the memory hardware. The following are the major activities of an operating system with respect to error handling. The operating system constantly checks for possible errors. The operating system takes an appropriate action to ensure correct and consistent computing. Resource management. The major activities of an operating system with respect to resource management are: the operating system manages all kinds of resources using schedulers. CPU scheduling algorithms are used for better utilization of CPU. Logging. The operating system keeps track of which programs use how much and what kinds of computer resources. Protection. Considering a computer system has multiple users and the concurrent execution of multiple processes, the various processes must be protected from each other's activities. Protection refers to a mechanism or a way to control the access of programs, processes, or users to the resources defined by a computer system. The following are the major activities of an operating system with respect to protection. The operating system ensures that all access to system resources is controlled. It ensures the external I/O devices are protected from invalid access attempts. It ensures authentication feature for each user. This figure shows one view of the various operating system services and how they interrelate. These services also make the programming task easier for the programmer. Let's take a look at the user and the operating system interface. First, the command interpreters. The shell is a type of program called an interpreter. An interpreter operates in a single loop. It accepts a command, interprets the command, executes the command, and then waits for another command. The shell displays a prompt to notify you that it is ready to accept your command. There are several types of shell: C shell, burning again shell, core shell. So this figure shows the burning again shell, which is a bash shell command interpreter being used on Mac. Graphic user interface. A GUI uses windows, icons, and menus to carry out commands such as opening, deleting, and moving files. Although a GUI operating system is primarily navigated using a mouse, a keyboard can also be used by keyboard shortcuts or the arrow keys. Many systems now include both CLI, command interpreter, and a GUI interface. Microsoft Windows is a GUI with a CLI command shell. Apple Mac OS X is a Aqua GUI interface with Unix kernel. Unix and Linux have a CLI with an optional GUI interface. A touchscreen interface is a combined display input device. The screen displays a graphical user interface, and the user's physical touching or voice is interpreted as an input or interaction with the interface. This figure shows the touchscreen of Apple iPhone. Both the iPad and the iPhone use the Springboard touchscreen interface. The user interface can vary from one system to another system. The factors affecting the choice of user interface, for example, storage space, ease of use, user experience, performance, efficiency, and the user requirement, etc. In this figure, it shows the Mac operating system GUI. A system call is the programmatic way in which a computer program requests a service from the kernel of the operating system it is executed on. A system call usually written in high-level languages such as C or C++. A computer program makes a system call when it makes a request to the operating system kernel. System call provides the service of the operating system to the user programs via Application Program Interface, API. It provides an interface between a process and the operating system to allow user-level process to request services of the operating system. Three most common API are Windows 32 API for Windows, POSIX API for Unix, Linux, and Macs, and the Java API for the Java Virtual Machine, JVM. Let's take a look at a system call to copy the contents of one file to another file. So cp in the Unix command is to copy file. The source file is in.txt. The destination file is out.txt. So we have several steps for the call sequence to finish. First, we acquire the input file name, and we write prompt to the screen and accept this input. Then we acquire the output file name. We write prompt to screen and accept input. Then we open the input file. If in.txt doesn't exist, we will abort this command and we will output the error message. If it exists, we create the output file. If out.txt is not available, we abort this command. So then we do a loop. We read from input file, write to output file. We do this loop until we finish all the readings from the input file. Then we close the output file and we write completion message to the screen to tell the user, and we terminate this call normally. As we see from the previous example, a simple program may make heavy use of the operating system, but the programmer never sees this level of details because usually application developers design programs according to an application programming interface, API. API is a connection between computers or between computer programs. A document or standard that describes how to build or use such a connection or interface is called an API specification. In Unix or Linux, if you type man read, man is a menu, read, so the read function will show first you must include the unit std.h in the program to use the read function. And for the definition of this function, first the return type, then its function name. After that are the parameters. So integer fd, that means the file descriptor to be read. Then we have a void buffer, that's a buffer into which the data will be read. Then we have the count, the size count, the maximum number of bytes to be read into the buffer. So when you call this function, you need to pass through 3 parameters, and this function will return the bytes to be read. If the bytes is -1, that means this function returns as error. The runtime environment is the environment in which a program or application is executed. It's the hardware and the software infrastructure that supports the running of a particular code base in real time. Runtime environment, RTE, provides a system call interface that serves as the link to system calls made available by the operating system. The system call interface intercepts function calls in the API and it invokes the necessary system calls within the operating system. Typically, a number is associated with each system call, and the system call interface maintains a table indexed according to these numbers. The system call interface then invokes the intended system call in the operating system kernel and returns the status of the system call. The caller need to know nothing about how the system call is implemented. We just need to obey to follow the API and understand what the operating system will do as a result of the execution of the system call. The kernel provides a set of interfaces by which processes running in user space can interact with the system. These interfaces give application controlled access to hardware, a mechanism with which to create new process and communicate with existing ones, and the capability to request other operating system resources. These API we call application programming interfaces act as the messengers between applications and the kernel. The applications issue issues various requests and the kernel fulfills them or return an error. System call provides a layer between the hardware and the user space process. But the system calls and the APIs are not the same thing. API is basically a function definition that specifies how to obtain a specific service. You generally don't make system calls directly. Instead, you use an API. Each system call has a corresponding wrapping routing that specifies the API that the application program must use to invoke the system call. Wrapper routings are function definitions whose only purpose is to issue a system call. However, an API doesn't have to correspond to a system call. An API can offer its service directly in user mode without making any system call, or a single API function can make several different system calls. More so different API functions can invoke the same system call. An API defines a set of program interfaces used by applications. Those interfaces can be implemented as a system call, implemented through multiple system calls, or implemented without the use of system calls at all. The same API can exist on multiple systems and provide the same interface to applications, while the implementation of the API itself can differ greatly from system to system. So from the programmer's perspective, the distinction between API and the system call is irrelevant. To them, it's just another function call. All he or she needs to think about is the function name, parameter type, and the return values. From the kernel designer's point of view, the distinction obviously is very significant. This figure shows how the operating system handles a user application invoking the open system call. So open is a system call used to provide access to a file in a file system and so on. There are three general methods used to pass parameters to the operating system. The simplest one is to pass parameters in register. If there are more parameters than the number of registers, block or table can be used. The address of the block will be passed as the parameter. In Linux, if there are more than 5 parameters, the block method is used. Parameter can be placed or pushed onto a stack by the program and popped off the stack by the operating system. So some operating systems prefer the block or stack method because the number of length of the parameters that are being passed are not limited. In this figure, we can see X represents the parameters for the system call. Then we load those parameters into a block, and we pass the address of the block into the register. Then we pass this, which is the address of the block. From this address, the system call can get the parameters. Here are the types of system calls. First, we have a process control. These system calls deal with process such as process creation, process termination. If a program has something wrong, a dump memory will be used and the error message will be displayed. Also, it has a debugger for determining bugs, single-step execution. Also have logs for managing access to shared data between processes. In Windows, for example, it has a create process, exit process, waiting for single object, system calls. And for Unix, it is like a fork, exit, and wait. File management. These system calls are responsible for file manipulation, such as creating a file, reading a file, writing into a file, etc. So we can see in Windows, we have system calls for the file management, create file, read file, write file, close handle. In Linux, it is open, read, write, and close. For device management, these system calls are responsible for device manipulation, such as reading from device buffers, writing into device buffers. So in Windows, for the device management, we have set console mode, read console, write console. In Linux, we have IOC-TL, read, write. Information maintenance. This system call handle information and its transfer between the operating system and the user program. In Windows, we have get current process ID, set timer, sleep. And in Linux, we have get PID, alarm, sleep. For the communication system call, these are useful for inter-process communication. They also deal with creating and deleting a communication connection. So in Windows, we have create pipe, create file mapping, map view of file. In Linux, we have pipe, SHM open, and MMAP. The protection system calls are used to control access to resources, get and set permissions, allow and deny user access. In Windows, we have set file security, initialize security descriptor, set security descriptor group. And in Linux, correspondingly, we have a chmod, umask, then chown. The standard C library provides system call interface. For example, we see printf statement in this C program. The C library intercepts this call and it invokes the necessary system call. So here, the system call write will be used. And the C library takes the value returned by the write system call and pass it back to the user program. There are many variations in process control. Let's take a look to example. The first example is the Arduino, which is a single tasking system. The Arduino is a simple hardware platform consisting of a microcontroller along with the input sensors that correspond to a variety of events such as change to light, temperature, and pressure, etc. To write a program for Arduino, we first write the program on a PC, then upload the compiled program known as a sketch from the PC to Arduino's flash memory via USB connection. The standard Arduino platform doesn't provide an operating system. Instead, a small piece of software known as a bootloader loads the sketch into a specific region in the Arduino memory. Once the sketch has been loaded, it begins running, waiting for the event that is programmed to respond to. For example, if the Arduino's temperature sensor detects that the temperature has exceeded a certain threshold, the sketch may have the Arduino start motor for a fan. And Arduino is considered a single tasking system, as only one sketch can be present in memory at a time. If another sketch is loaded, it replaces the existing sketch. Furthermore, the Arduino provides no user interface beyond hardware input sensors. FreeBSD is an example of a multitasking system. When a user logs onto the system, the shell of the user's choice is running, waiting commands and running programs the user requests. Since FreeBSD is a multitasking system, the command interpreter may continue running while another program is executed. To start a new process, the shell executes fork system call. Then the select program is loaded into memory by an exec execute system call, and the program is executed. Depending on how the command was issued, the shell then either waits for the process to finish or run the process in the background. When the process runs in the background, it cannot receive input directly from the keyboard because the shell is using this resource. The I/O is therefore done through files or through a GUI interface. Meanwhile, the user is free to ask the shell to run another program or to monitor the progress of the running process or to change that program's priority and so on. When the process is done, first it will execute the exit system call. If everything is okay, it will return the status of code 0. If there error, it will return a non-zero error code. Another aspect of a modern system is its collection of system services. In computer hierarchy, at the lowest level, it is the hardware. Next is the operating system, then the system services, and finally, the application programs. System services, also known as the system utilities, provide a convenient environment for program development and execution. Some of them are simple user interface to system calls. Others are considered more complex. They can be divided into these categories. File management. These programs create, delete, copy, rename, print, list, and generally access and manipulate files and directories. Status information. Some programs simply ask system for the date, time, amount of available memory or disk space, number of users, or similar status information. Others are more complex, providing detailed performance, logging, and debugging information. Typically, these programs format and print the output to the terminal or other output devices or files, or displayed in a window of the GUI. Some systems also support registry, which is used to store and retrieve configuration information. File modification. Several text editors may be available to create and modify the content of files. There are also special commands to search content of files. Programming languages support, like compilers, assembly, debugger. We have learned like C++, Java, right? Those are supporters for those high-level programming languages. Program loading and execution. Once a program is assembled or compiled, it must be loaded into memory or to be executed. The system may provide absolute loaders, relocatable loaders, linkage editors, and overlay loaders. Debugger systems for either high-level languages or machine languages are needed as well. Communications. These programs provide a mechanism for creating virtual connections among process, users, and computer systems. They allow users to send messages to one another's screen, to browse web pages, to send email messages, to log in remotely, or to transfer files from one machine to another. A background service performs an operation that isn't directly noticed by the user. So those running system program process are known as the services or subsystems or daemons. One example is network daemon. Another example is a process schedulers. The background services can be launched at the boot time. Some of these processes terminate after completing their tasks, while others continue to run. There are also application programs which are not considered part of operating system. Those application programs are run by the users and launched by the command line or GUI interface. Source files are compiled into object files. that are designed to be loaded into any physical memory location, a format known as a relocatable object file. Then next, the linker combines these relocatable object files into a single binary executable file. During the linking phase, other object files or libraries may be included as well, such as standard C or math library. A loader is used to load the binary executable file into memory, where it is eligible to run on a CPU core. An activity associated with linking and the loading is relocation, which assigns final address to the program part and adjusts code and the data in the program to match those addresses, so that, for example, the code can call library functions and access its variables as it executes. Nowadays, most systems allow programs to dynamically link libraries as the program is loaded. Windows, for example, supports dynamic linked libraries, DLL. The benefit of this approach is that it avoids linking in the loading libraries that may end up not being used into an executable file. So instead, the library is conditionally linked and is loaded if it is required during program runtime. In this figure, we can see we have a C program called main.c. So this is the source program. And then we call the compiler, so we use gcc command, gcc-c main.c. Then it will generate the object file main.o. Then we call the linker, which is gcc-o main-o-lm. It generates the executable file main, because in the linker phase, we need to link other object files. Then after the executable file is generated, we type in the command /main. So this shell first creates a new process to run the program using the fork system call, F-O-R-K, fork system call. The shell then invoke the loader with a exec, execute system call. In the passing exec, the system call the name of the executable file. The loader then loads the specified program into memory using the address space of newly created process. We also see the dynamically linked library. So the math library is not linked into the executable file main. Rather, the linker inserts relocation information that allows it to be dynamically linked and loaded as the program is loaded. It is also possible for multiple processes to share dynamically linked libraries, resulting in significant savings in memory use. When we are considering design the operating system, basically we have two goals, user goals and the system goals. For the user goals, operating system should be convenient to use, easy to learn, reliable, safe, and fast. For the system goals, operating system should be easy to design, implement, and maintain, as well as flexible, reliable, error-free, and efficient. Specifying and designing an operating system is a highly creative task in software engineering. Policies are ways to choose which activities to perform. Mechanisms are the implementation that enforce policies, and often depend on some extent on the hardware on which the operating system runs. For example, the timer construct is a mechanism for ensuring CPU protection. But deciding how long the timer is set to be for a particular user is a policy decision. Why should we separate policies and the mechanisms? Decoupling the mechanism implementations from the policy specifications makes it possible for different applications to use the same mechanism implementations with different policies. So this means that those mechanisms are likely to better meet the needs of a wider range of users for a longer period of time. Once an operating system is designed, it must be implemented. Usually, the lowest levels of the kernel might be written in assembly language in C because low-level language are faster, very efficient the speed. The higher-level routines might be written in C and C++, and the system libraries might be written in C++ or even higher-level languages. Because for higher-level language, the programmer is human. For higher-level language, it's usually easy to understand and debug. The code can be written faster and more compact. The drawback is the higher-level language is slower and it requires more storage, but the operating system implemented with high-level language is far easier to port to other hardware. The modern operating system is very large and a complex program. There are various ways to structure ones. For a simple structure, example is MS-DOS. For more complex than Unix, we have a layered approach in which the operating system is broken into a number of layers. An operating system layer is an implementation of an abstract object made of data and operations that can manipulate those data. The MACH, M-A-C-H, is the modularized kernel using the microkernel approach. The monolithic operating system is a very basic operating system in which file management, memory management, device management, and process management are directly controlled within the kernel. The kernel can access all the resources present in the system. The original Unix is the monolithic operating system. The original Unix operating system has two separate parts, the kernel and the system programs. The kernel is further separated into a series of interfaces and the device drivers, which have been added and expanded over the years as Unix has evolved. Everything below the system call interface and above the physical hardware is the kernel. The kernel provides the file system, CPU scheduling, memory management, and the other operating system functions through system calls. All those functionality are combined into one single address space. The Linux operating system is based on Unix and is structured similarly. In this figure, we can see that applications typically use glibc standard C library when communicating with the system call interface to the kernel. The Linux kernel is a monolithic in that it runs entirely in kernel mode in a single address space. It does have a module design that allows the kernel to be modified during runtime. We can see monolithic kernel is hard to extend, but they have very good performance. It's fast and it requires very little overhead in system call interface. They run in kernel mode, so the communications in the kernel are very efficient. The monolithic approach is often known as a tightly coupled system, because change to one part of the system can have wider-ranging effects on other parts, and we can design a loosely coupled system. So one method is a layered approach, in which the operating system is broken into a number of layers or levels. The bottom layer, which is layer 0, is the hardware. The highest, the layer N, is the user interface. In this module design, one change in one component affects only that component and no others, allowing system implementers more freedom in creating and changing the inner workings of the system. An operating system layer is an implementation of an abstract object made of data and operations that can manipulate those data. A typical operating system layer, say layer M, consists of data structures and a set of functions that can be invoked by higher level layers. Layer M, in turn, can invoke operations on lower level layers. This approach simplifies debugging and system verification. The approach's drawback is the speed is poor due to overhead of requiring a user program to traverse through multiple layers to obtain an operating system service. Modern operating systems have fewer layers with more functionality, providing most of the advantages of modularized code while avoiding the problems of layer definition and interaction. MACH, MARC, developed by Carnegie Mellon University, modularized the kernel using the microkernel approach. A microkernel comprises only the core functionalities of the system. A monolithic kernel is large process running in a single address space, whereas microkernel can be broken down into separate processes called servers. Microkernel architecture is small and isolated, therefore it can function better. Microkernels are secure because only those components that included that disrupt the functionality of the system otherwise. The expansion of the system is more accessible, so it can be added to the system application without disturbing the kernels. Microkernels are modular, and the different modules can be replaced, reloaded, modified, without even touching the kernel. Disadvantages of microkernels are it provides service in a microkernel system are expensive compared to the normal monolithic system. Context switch or a function call needed when the drivers are implemented as procedures or process, respectively. The performance of a microkernel system can be indifferent and it may lead to some problems. So it requires more overhead than monolithic system. This figure shows the architecture of a typical microkernel. The structure removes all non-essential components from the kernel and implements them as a user-level programs that reside in separate address spaces. The result is a smaller kernel. Microkernels provide minimal process and memory management in addition to a communication facility. A loadable kernel module, LKM, is an object file that contains code to extend the running kernel, or so-called base kernel, of an operating system. LKMs are typically used to add support for new hardware, for example, device drivers, or file systems, or for adding system calls. Linux uses loadable kernel modules, primarily for supporting device drivers in the file systems. LKM can be inserted into the kernel as the system is started or booted, or during runtime, such as when the USB device is plugged into the running machine. If the Linux kernel doesn't have the necessary driver, it can be dynamically loaded. LKM can also be removed from the kernel during runtime as well. In practice, very few operating systems adopt a single, strictly defined structure. Instead, they combine different structures, resulting in hybrid systems that address performance, security, usability issues. For example, Linux is monolithic because having the operating system in a single address space provides very efficient performance. However, it is also modular, so that the new functionalities can be dynamically added to the kernel. Windows is largely monolithic as well, again it's for performance reason, but it retains some behavior typical of microkernel systems, including providing support for separate subsystems known as operating system personalities that run as the user mode process. Windows system also provides support for dynamically loadable kernel modules. Apple's Mac OS operating system is designed to run primarily on desktop and the laptop computer system, while iOS is a mobile operating system designed for the iPhone and the iPad. This figure shows the general architecture of them. User experience layer defines the software interface that allows the user to interact with the computing devices. Mac OS uses Aqua user interface, which is designed for a mouse or trackpad, while iOS uses the Springboard user interface, which is designed for touch devices. Application frameworks layer include the Coca and the Coca Touch frameworks, which provide an API for the Object-C and the Swift programming languages. Mac OS use Coca and the iOS use a Coca Touch. Core frameworks. This layer defines frameworks that support graphics and the media including QuickTime and the OpenGL. Kernel environment. This environment, also known as a Darwin, includes the Mac microkernel and the BSD Unix kernel. As we see from this figure, applications can be designed to take advantage of user experience features or to bypass them and interact directly with either the application framework or the core framework. Additionally, an application can forego frameworks entirely and communicate directly with the kernel environment. Darwin uses a hybrid structure. It provides two system call interfaces, Mark system calls, also known as the traps, and the BSD system calls, which provides POSIX functionality. Beneath the system call interface, Mark provides fundamental operating system services, including memory management, CPU scheduling, and inter-process communication facilities such as message passing and remote procedure calls. Many of these functionalities provided by Mac is available through kernel abstractions, which include tasks, threads, memory objects, and pods. In addition to Mark and BSD, the kernel environment provides an I/O kit for development of device drivers and dynamically loadable modules, which Mac OS refers to as a kernel extensions. Mac OS is intended for desktop and the laptop computer system, Macintosh. It is combined to run on Intel architectures. iOS is designed for mobile devices for iPhone and iPad. This is compiled for ARM-based architectures. It uses a Coca Touch Object-C API for developing apps. Media services layer for graphics, audio, and video. Also, the core services provides cloud computing database. Android is a mobile operating system based on modified version of Linux kernel and other open source software, designed primarily for touchscreen mobile devices such as smartphones and tablets. Android is developed by Open Handset Alliance and Google. Google has developed separate Android API for Java development. Java applications are compiled into a form that can execute on the Android Runtime ART, a virtual machine designed for Android and optimized for mobile devices with limited memory and CPU processing capability. Java programs are first compiled into a Java bytecode .class file and then translated into an executable .dex file. Android Runtime ART performs ahead-of-time AOT compilation. .dex files are compiled into native machine code when they are installed on a device, from which they can execute on the ART. AOT compilation allows more efficient application execution as well as reduced power consumption, features that are crucial for mobile systems. The set of native libraries available for Android applications include frameworks for developing web browsers, WebKit, database support, SQL, SQLite, and network support, such as a secure socket, SSLS. Because Android can run on almost unlimited number of hardware devices, Google has chosen to abstract the physical hardware through the Hardware Abstraction Layer, HAL. Linux uses glibc library. Google instead developed the Bionic standard C library for Android. Not only does Bionic have a smaller memory footprint than glibc, but it also has been designed for the slower CPUs that categorized mobile devices. At the bottom of Android software stack is the Linux kernel. Google has modified this Linux kernel to support mobile systems. It also made changes in memory management and allocation and add a new form of IPC known as a binder. When you buy a new computer, the operating system is already installed in the computer. If you are a developer and you are generating from scratch, you must follow these steps. 1. Write the operating system source code or obtain previously written source code. 2. Configure the operating system for the system on which it will run. 3. Compile the operating system. 4. Install the operating system. 5. Boot the computer in its new operating system. The following steps is to build a Linux system from scratch. First, you download the Linux source code from kernel.org. Then configure the kernel using make manuconfig command. Then compile the main kernel using the make command. Then compile the kernel modules using make modules. Use the command make module install to install the kernel module into VM Linux. Install the new kernel on the system by entering the make install command. On most systems, the boot process proceeds as follows. 1. A small piece of code known as a bootstrap program or bootloaders locates the kernel. The program that starts the chain reaction that ends with entire operating system being loaded is the bootloader or bootstrap loader. The bootloader's only job is to load other software for the operating system to start. So at the beginning, a small bootloader located in the non-volatile firmware known as BIOS is run. BIOS, BIOS, Basic Input-Output System, performs a series of activities or functionality tests. Many recent computer systems have replaced the BIOS-based boot process with a UEFI, Unified Extensible Firmware Interface. UEFI has several advantages over BIOS, including better support for 64-bit systems and larger disks. The advantage of UEFI is it is a single, complete boot manager, and therefore is faster than the multi-stage BIOS boot process. The BIOS boot process sometimes involves two-step process. The first one is boot block at a fixed location is loaded by ROM code, then loads the bootstrap loader from disk. After booting from BIOS or UEFI, if all the diagnostic test returns OK, the bootstraps can also initialize all aspects of the system from CPU registers to device controls and the contents of main memory. So it starts the operating system and mounts the root file system. Now the system is set to be running. Grub, GRUB, is an open source bootstrap program for Linux and the Unix system. Boot parameters for the system are set in a grub configuration file, which is very flexible and allows changes to be made at the boot time, including modifying kernel parameters and even selecting among different kernels that can be booted. Bootloaders for most operating systems, including Windows, Linux, and Mac OS, as well as both iOS and Android, providing booting into recovery mode or single-user mode for diagnosing hardware issues, fixing corrupt file systems, and even reinstalling the operating system. Debugging is the process of finding the problems in a computer system and resolve it. It can also include performance tuning, which seeks to improve performance by removing processing bottlenecks. There are many different ways in which operating systems perform debugging. Some of these are log files. The log files record all the events that occur in an operating system. This is done by writing all the message into a log file. Call dump files. The call dump files contain the memory address space of a process that terminates unexpectedly. The creation of call dump is triggered in response to program crashes by the kernel. The call dump files are used by the developers to find the program state at the time of its termination so that they can find out why the termination occurred. Crash dump files. In the event of a total system failure, the information about the state of the operating system is captured in crash dump files. Trace listing. The trace listing records information about a program execution using logging. This information is used by programmers to debugging. System administrators and the technical personnel can use the trace listing to find the common problems with software using software monitoring tools. Profiling. This is a type of program analysis that measures various parameters in a program, such as space and the time complexity, frequency, and the duration of function calls, usage of specific instructions, etc. Profiling is done by monitoring the source code of the required system program using a code profile. A system performance monitor, SPM, collects and reports key performance indicators and the metrics into the operational state of a system. Most operating systems have native SPM application or component that display factual and graphical stats for system performance. This figure shows Windows Task Manager, a tool that includes information for current applications as well as process, CPU, and memory usage and the networking statistics. Tracing tools collect data for a specific event, such as the steps involved in system call invocation. The following are examples of Linux commands that trace events. Strace is trace system calls invoked by a process. GDB is GNU debugger. This tool helps to debug the programs written in C, C++, etc. PERF is a collection of Linux performance tools. TCP dump is widely used in network packet sniffers. BCC is a toolkit for creating efficient kernel tracing and manipulation programs, and it includes several useful tools and examples. It makes use of extended BPF, Berkeley Packet Filters, formerly known as a eBPF, a new feature that was first added to Linux 3.15. Much of what BCC uses requires Linux 4.1 and above. BCC makes BPF programs easy to write, with kernel instrumentation in C and the front ends in Python. It is suited for many tasks, including performance analysis and the network traffic control. As an example, the BCC Dick Snoop tool traces disk I/O activity. So if we type the command /disk/snoop.py, so it's a Python file, it generates the following example output. This output tells us the timestamp when the I/O operations occurred, whether the I/O was read or write operation, and how many bytes were involved in the I/O. The final column reflects the duration in milliseconds of the I/O. What makes BCC especially powerful is that its tools can be used on live production systems that run in critical applications without causing harm to the system. This is particularly useful for system administrators who must monitor system performance to identify possible bottlenecks or security exploits. This figure illustrates the wide range of tools currently provided by BCC and the eBPF and their ability to trace essentially any area of the Linux operating system. BCC is a rapidly changing technology with new features constantly being added.